test. Okay. So any question, guys, regarding gas turbine? Turbine gas turbine plant. Any question? Tak ada? Is there any particular question on gas turbine yang nak tanya? Tak ada ke? Ya, good afternoon juga. Okay, kalau tak ada, kita lihatlah apa yang kita belajar tentang gas turbine. Ya. The first thing yang we learn about gas turbine, they're very simple Brayton cycle. Okay, Brayton cycle consists of a very simple one, consists of compressor, and we have a turbine. We have a combustion chamber, exhaust, intake, and this is the output of our turbine to be driven a electrical generator. So this is the compressor, this is the turbine. So this is state 1, state 2, state 3, and state 4. So this is our combustion chamber. And when we sketch on the TS diagram, so this is a very simple one. So this is our compression process. This is our expansion process in the turbine. Okay, when we incorporate with the isentropic efficiency, when we incorporate isentropic efficiency on the turbine, so what we could have is this is 0.1, this is 0.2s, this is 2, this is 3, this is 4s, and this is 4. It is a very simple one. So the process begin at 1 and end at 4. Okay, there's no connection between 4 and 1. There's no arrow, there's no process, because at 1 we are going to induce a new fresh charge of air. So as far as the work net is concerned, we are going to get the work net as the work for the turbine minus work for the compressor, whereby work for the turbine is work 3, 4, work for the compressor is work 1, 2. And then for the Q in is involving the Q 2, 3. And to look at the quality of this turbine cycle, which we refer as the thermal efficiency, this should be our W net divided by Q in. So this is what we have, a very simple one. And then after that, we want to increase the work net. In order to increase the work net, what we are going to do is we are going to have the multi-stage of compression, multi-stage of expansion with reheat. Okay, so the second one what we have right here is the turbine, the compressor, and then we have turbine, we have another turbine, right? And then we have the reheat process in between the expansion. Of course, right here we are going to have our combustion chamber. So this is your compressor, this is your turbine high pressure, this is the turbine low pressure. Of course, our W net is running a electrical generator. This is state 1, state 2, state 3, state 4, state 5, and state 6. Okay, this is 5, 6. Alright, this is to increase the W net. Right, and at the same time also we are going to increase the WQ, the Q in. So we have extra Q, Q4, 5. So this should be our combustion chamber 1. This should be our combustion chamber number 2. And if we sketch on the TS diagram, so we have the heat process. This is our reheat. the intermediate pressure between turbine high pressure and turbine low pressure. So this is our process, compression process. And then we have our Q in expansion process, high pressure turbine, and we have the second process for our expansion at the low pressure turbine. Okay, if we don't have any reheat, so this should be our end of our process of the turbine. If there is no reheat, still incorporate the high pressure turbine and low pressure turbine. So this is the temperature. Okay, and in this case, how to get the W net? The W net is equal to W sigma W of the turbine minus W for the compressor. So both stage of work minus this. And then we could have also the same reheat process, but the arrangement is different. But as far as the TS diagram is concerned, it's still the same. We could arrange, right? We could arrange our plant having two shafts. Okay, so combustion chamber, again, this is our combustion chamber before entering the second turbine. So this is our compressor, this is our turbine high pressure, turbine low pressure. This is our CC1, this is our CC2, this is the flow. This is the intake. 1, 2, 3, 4, 5, and 6. Okay, so if you look right here, the states is still 6. The first one is still 6. This one also still 6. As far as this TS diagram is concerned, it's valid for both. Okay, valid for both schematic or plan. But what we could have extra for this plan is the work. We can see that the work for turbine high pressure is equal to the work to the compressor. Right, and then the W net is equal to what? Is equal to the summation of all the work, which is the work for the turbine high pressure plus the work for turbine low pressure minus W compressor. And the work compressor is equal to work turbine high pressure, so this is cancelled off. So what we can have is the W net is equal to the W low turbine expansion. Okay, so that is our W net. And for the Q, same for the both layout, schematic. What is the Q in? The Q in is equal to QQ for C1 plus the Q for CC2. From here, we could get what is the thermal efficiency, which is equal to the W net divided by the Q in. Okay. So if we have the mechanical efficiency right here, where do we put our mechanical efficiency at this equation? Guys, if we have a mechanical efficiency at the power shaft, this is also known as a power shaft. The turbine high pressure running or driving the generator. So if we have the W net is equal to WTLP, and if we have the mechanical efficiency, where do we put the mechanical efficiency? The left or the right? Guys, where do we put our mechanical efficiency at the power shaft?
Both.
Huh? Putting both? What is the definition of mechanical efficiency? efficiency. What is the definition of efficiency? Desired output. Which is our desired output? So this should be our W net right here. So what is our desired output? The desired output is W net, and the required input is a W for turbine low pressure. So meaning that we are going to put the mechanical efficiency at this side, to the right. Okay, so always look what is our definition of our efficiency. Desired output divided by required input. So this is our desired output, which is the W net, and this is our required input, which is the W turbine low pressure. So this is how we put our mechanical efficiency. Same goes for this. So if we have right here, for the turbine, the shaft for compressor, so where do we put our mechanical efficiency? So what is the definition? The definition for this shaft, the desired output. What is the desired output? The output needed by the compressor, and what is the desired input? Is the W for the turbine high pressure. So in this case, we are going to put the mechanical efficiency is towards at the WT. This is the mechanical efficiency. Yeah, from here, this is how you get or you put your mechanical efficiency. Always look what is the desired output divided by required input. Why do we have mechanical efficiency? Guys, why do we have the mechanical efficiency?
Due to the transmission, sir.
Yeah, because of the transmission losses or the friction. Okay, maybe we are using some gearing system towards the shaft. So that is one of the reasons why we have the mechanical efficiency, because we have losses through the work transmitted, usually due to friction. Okay, usually due to friction. And then after this, what we have, we could look here. When we have reheat process, the temperature exhaust is higher than compared with the without any reheat. So we have higher temperature at the exit of the turbine when we have reheat process compared to the non-reheat process. So meaning that we are going to use this high pressure in exhaust gas to be used to heat up the air after the compression process. Right? But before that, let's look into the second method. How do we increase the W net? Okay, this is where we look at the compression side. So if we look at the compression side, we have multiple compression process. Let's say this is our turbine. This is our output. The multi-stage compression with reheat. And we have our compression process with intercooler. Compressor, low pressure, compressor, high pressure, turbine, high pressure, turbine, low pressure. CC1, CC2, this is our intercooler. Okay, so what happened? We can see that we have reduced the compression process or the compression work at the second compressor, which in this case is the compressor high pressure. So what we have, this type of cycle. Okay, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8. Okay, so this is the direction. Okay, so as far as the W net is concerned, what is W net? The W net is equal to the sigma work from the turbine. Okay, sigma work of the turbine minus the sigma work of the compressor, plus these two turbine work minus these two compressor work, so we get the W net. So here is our W net. Okay, so if you compare the compression process without any intercooler, so this is where we are going to have our pore, right, higher. But when we have intercooler, this is what we have. The Q in is rather greater without any intercooler, or with compared with or to the intercooler, right? So this is the process of the Q in starting from 4 to 5. Increase in Q in without intercooler 4 to 5. But in this case, we are going to increase the W net. So as far as the W net is concerned, we are going to have more W net when we have the multi-stage compression with intercooler, because we can reduce the work at 3 to 4. Okay? And then also we have two characteristics whereby we could have T3 is equal to T1. When T3 is equal to T1, what does this refer to?
Complete intercooler.
Bukan complete intercooler.
Intercooling.
Complete intercooling.
Intercooling.
Okay, complete intercooling. So this is first characteristic. Number two, what do we have is same pressure ratio between two stages of compression. P2 over P1 is equal to P4 over P3. What does this refer to?
Minimum work input.
No, this is same pressure ratio. Okay, same pressure ratio. When we have both characteristics in one plant, this will refer as the work minimum for compression process. Okay, so when we have this work minimum for compression process, whereby the plant or the schematic diagram valid, there is T3 equal to T1 complete intercooling, and we have P2 over P1 equal to P4 over P3, which is same pressure ratio. When we combine these two characteristics, then we get the minimum work input for the compression process. So this is the requirement to have a work minimum input to the compression process. Okay, same pressure ratio, complete intercooling. If this plant is only valid only one complete intercooling, so we cannot assume that the P2 over P1 equal to P4 over P3. Okay, so if one of them is not being fulfilled, then you have to get the individual work for the compression process. Right? So for a minimum compression process, then we can combine the work. The compressor is equal to the 2 times the work for low pressure or 1, 2 equal to 2 multiplied by work for 3, 4. Why? Because when we have this minimum work characteristic, we are going to have the T3 equal to T1, and then we are also going to have the T4 equal to T2. That's why we can use this formula. Okay? So if the number one is not being fulfilled, then you have to get the work for the compressor is equal to work 1, 2 plus work 3, 4. If only the number two is not been fulfilled, again, you need to get the individual work. You cannot combine as this. Okay, this work compressor equal to 2 multiplied by work 1, 2, or 2 multiplied by work 3, 4. This is only for both cases is being fulfilled at the same plant. Right? At the same plant. So take care of that. So again, we could have a different arrangement of the shaft. Different arrangement of the shaft. In this case, we have only one shaft, therefore the W net is equal to the summation of work for the compressor and the summation of work of the compressor. We minus them. Deduct the compressor work. So we get the W net. But we could also have the same plant with different arrangement. What is the different arrangement? Okay, let us see. Maybe we have this two shaft. This is the possibility of the arrangement we could have. Right? And then this is our W net. So the compressor, this is turbine, this is turbine. Low pressure, number one. Okay, this is low pressure, this is high pressure, this is high pressure, this is low pressure. Right? So in this case, what is W net? The W net is equal to work for turbine, low pressure, minus work for the compressor, low pressure. So that is our W net. Of course, right here, we are going to have the combustion chamber, and also we could have the reheat process. And we also could have the intercooling process. This is the intercooling. Right? So as far as the TS diagram is concerned, we are going to have the same TS diagram. Okay, we are going to have the same TS diagram, but the arrangement is different. So what does this arrangement imply? The arrangement implies that we could get the relationship between the turbine and compression and the compressor work. Whereby in this case, we are going to have number one, the W. Okay, the W compressor high pressure is equal to the W turbine high pressure. Right? But in this case, we use this for this shaft. W net equal to WTLP minus WCLP. This is combustion chamber number one. This is combustion chamber number two. And we could have another arrangement. What arrangement that you think that we could have? We could have one turbine driving both compressors. And the last turbine is called as the power turbine. Maybe we could have right here our reheat. Okay, input, intercooler, combustion chamber, W net. Compressor low pressure, compressor high pressure, CC1, turbine high pressure, turbine low pressure, CC2, intercooler. We have different arrangement, okay, different arrangement. But as far as the TS diagram is concerned, it's still the same. So in this case, what is the work relationship that we can write? We could find that the turbine high pressure work is equal to the compressor low pressure work plus the compressor for high pressure. And in this case, what is W net? W net is equal to WTLP. And of course, the Q in is equal to QCC1 plus QCC2. Right? So this is the arrangement we could get in order to increase our work net. Okay, to increase our work net. This is using this multi-stage compression with intercooler and also reheat. The purpose is to increase the W net. And then the last modification that we could get is to look at the use of high temperature gas exit from the turbine high pressure or the turbine by using what we call as the heat exchanger. Okay, heat exchanger. And of course, what is the purpose of the heat exchanger? And the heat exchanger is to reduce the heat input to the plant. So this is the case whereby we are going to increase the thermal efficiency. And how we do it? By reducing the Q in. Then we get the greater thermal efficiency. Okay? So again, we have the same intercooler for the compressor. And then after the last compressor, we are going to have a heat exchanger. And after that, we are going to have combustion chamber. And then we have of course, the turbine, high pressure, low pressure. We have one shaft. Okay, only one shaft. And this is our W net. Compressor, low pressure, compressor, high pressure. This is our intercooler. Okay, IC, intercooler. This is our heat exchanger. Right? So before entering the second turbine, low pressure, we are going to have reheat. And because of the reheat process, the exhaust gas temperature is going up. So what are we going to do? We are going to make use of this exhaust gas temperature or heat in order to heat up the air after the compression process. So this is our heat exchanger. So we have of state 1, state 2, then state 3, state 4, state 5, state 6, state 7, state 8, state 9, and state 10. So this is the arrangement that we could have. Okay? And we could have also another arrangement. Let's say we have 3 turbines. Okay, 3 turbines. So if we had 3 turbines, what do you think that we could arrange? First turbine is driving the compressor. Second turbine also driving another compressor. Right? And we have the last turbine is totally to produce, mainly to produce the work net. So this is the arrangement that we could have. Right? So if you can put all the flow and the other component, so this is our first compression process, second compression process, heat exchange. You have the intercooler. So this is the intercooler. And then for the second compression process, then we put a heat exchanger. Now, of course, for each compression, for the first turbine, we must have a combustion chamber. And then for the second turbine, maybe we have a reheat. A reheat, go to the second turbine. And then maybe here also we could have a reheat. before entering the third turbine. And now we are going to reject the heat, and the rejected heat from the last turbine is going to be used to heat up the air after the last stage of compression. So this is our intercooler. Sorry. This is our intercooler. This is our heat exchanger. Now let us put how many states that we have in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we have isentropic efficiency for turbine, we have isentropic efficiency for compressor, then we have extra states. What is the extra state? Here we have 1, 2, 3, 4, 5. Okay, so meaning that we got 12 plus 5 equal to 17 states. Right? In other words, we have 17 temperature. Do you think that this type of question will come out for the test? Who knows? Right? Who knows? So, by incorporating the heat exchanger, what we could have right here is the, let me put the diagram first. How many expansion? 1, 2, and 3 expansion process. We have 2 compression. So this should be our first compression process. Intercooler, second compression process. We have our highest pressure right here. And then we are going to expand in the first compressor, first turbine. And then we have reheat. Second turbine, we have reheat, and we have third turbine. Okay, so because of this temperature is very high, then we can use this temperature to reheat, to heat up the air after coming out from the high pressure compressor. So the limit is what? The limit is to look at this point and this point. Okay, so this should be the level here. Maybe we could have the reheat, the heat exchanger process up to this point. It's in between these two values. Okay, these two limit, the minimum limit and the maximum limit, which we refer as the what? We refer this as the maximum possible available of temperature difference. Okay? We refer as the B. And this we refer as the increment of temperature, we refer as A. This is the maximum available temperature or the maximum available temperature difference. So to get what is the heat up air temperature right here, we need to look at the ratio of A over B, which is usually given, and this is given the name as what? Guys, what is the name of this A over B? What is the ratio? Thermal ratio. Okay, thermal ratio. So in this case, let us put all the states 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let me check whether I'm getting the right. Yeah, the last one is, oh sorry, it's not 11, but the last one is 12. What is 12? 12 is the exhaust gas temperature. So this is 12. Right? So this is our compressor low pressure, compressor high pressure. This is turbine high pressure. This is turbine intermediate pressure. This is turbine low pressure. 6, 7 high pressure, 8, 9 is the intermediate pressure, 10, 11 is the low pressure. Okay, and then to get what is T5, we need to get from this thermal ratio what is A. A is a T5 minus T4 divided by B. B is T11. So T11 minus T4. So this is where the formula is being used to get the T5. So in order to get the T5, you need to know what is T11. Okay, you need to get what is T11. Meaning that you need to get all the temperatures except 5. Right? State 5, temperature T5 only can be obtained when we have the T11. Right? So in this case, we could use all the relationship between the work input and work output for the turbine, and also for this power shaft. From here, we could have from this shaft, W compressor high pressure is equal to the W turbine high pressure from this shaft. From this shaft, we can get the W compressor low pressure is equal to the W turbine intermediate pressure. From this shaft, we are going to have the W turbine low pressure is equal to W net. So this is the relationship between the work turbine compressor and the work net by looking at the shaft. If you make your W net, okay, if you make or you look at your W net equal to the summation of work, you will get the same value or the same formula for W net. So right here, we could get the W turbine high pressure plus W turbine low pressure plus, sorry, intermediate pressure first. The intermediate pressure plus W turbine low pressure. And then this is minus W compressor high pressure minus W compressor low pressure. Then we know that the turbine high pressure is running the compressor high pressure. The turbine intermediate pressure is running the compressor low pressure. So at last, what we could have W net is equal to WT LP. It's what we have right here. Okay. And in this case, we are going to have the overall pressure ratio. What is our overall pressure ratio? What is the Pmax over Pmin, which is called as the overall pressure ratio. If we look at the compressor side, we are going to have the P4 over P1. If we look at the expansion side, this is P6 divided by P11. And we look at the relationship between the pressure ratio for the compression side, we could have the P2 over P1 is equal to P4 over P3. So this is the pressure ratio if you look at the compression side. If you look at the pressure ratio relationship at the expansion side, at the turbine, what we could have is the P6 over P7, right? Sorry, the overall pressure ratio. The overall pressure ratio is P6 over P11 equal to P6 over P7 multiplied by P8 over P9 multiplied by P10 over P11. Okay, and our Q in, where is our Q in? Our Q in here is from 5 to 6, Q in 7 to 8, Q in 9 to 10. So what is our Q in? Q in is equal to Q 5 to 6 plus Q 7 to 8 plus Q 9 to 10. This is involving what? Involving the combustion chamber 1, combustion chamber 2, combustion chamber 3. Okay? And if you want to get what is the value of T12, as I mentioned in the class, the T12 is only obtained, or we could determine the T12 if the question asks for the value of T12. And this is equal to what? This is equal to T11 minus T12 divided by T11 minus T4. This case, this is the increment of the temperature for air after the last compression process, but this is the equivalent to the drop of temperature for the exhaust side. Okay, T11 minus T12 divided by T11 minus T4. So from this equation, is purposely to get T5, and this equation is purposely to get T12. Okay? Any question, guys? So just look at some example right here. This is for the question 1819. This is the latest question for test, for test. Latest question for test on turbine. So if you look yourself, I will give you this latest test 3 for 18-19-02. So this is, if you look right here, this set is looking at what? Looking at the multi-stage compression with intercooler, and also the multi-stage expansion with reheat. So this is the diagram. One shaft, two shaft. We have compressor shaft, we have power shaft. Okay, that is for the 18-19. If you look at 15-16, this is the most features, the most featured type of our plant. You see, we have our intercooler, we have our combustion chamber, we have our regenerator or the heat exchanger, we have the reheat, right? So every element of modification, either to increase the work net or to increase, which one is to increase the work net? To increase the work net is basically multi-stage compression with intercooler. To increase the W net basically is also being contributed by the reheat. The only thing that we could get in terms of increasing the thermal efficiency is this regenerator. So if I could put individually, what is this does? This is the purpose of this intercooler is to increase the W net. For the generator is to increase the thermal efficiency. The reheat is to increase the W net. Okay, so 2 W net, 1 thermal efficiency. Okay, so if you look right here, if we put this diagram in terms of wording, then we could have a very lengthy type of question. But in this case, for this test, you are going to struggle with time because you have how many temperatures? In this case, you have 10 temperatures to be determined. Yeah, but except for the 10, if the question asks for the temperature of T10. See? Find the exhaust gas temperature of the plant. So we need the T10. So you have in total is 10 states, 10 temperatures. And then let us see, is there any isentropic efficiency? No, there is no isentropic efficiency. So you could have more time to solve it. But in this case, through my experience, you are going to have a very, very solid 45 minutes in order to solve this problem. Okay? Because this is the only question that we have incorporating all the features, the modification. And then for 16, 17, this is the time of our plant, whereby we have the heat exchanger, only one compressor, one turbine, W net, and one shaft, right? And then we have our combustion chamber right here. So, of course, this type of question, the schematic diagram looked very simple, but if you could look right here, you are going to have isentropic efficiency for both compressor and turbine. So that will take time also to solve it. Okay, so this is the type of question that we could have on the test. And the last one is this. We are going to this. So we have the all features, and then this one is basically we look at the usage of the heat exchanger, and this one is to look at the reheat, the reheat cycle. Okay. For 161702 and 151602 is already uploaded in my web page. You can have the solution in my web page. So what I'm going to give later on in the WhatsApp group, I'm going to give the question of test 2 for 181902, which I have. That is the latest version that I have in terms of the question for turbine. Okay, guys, I think that's it for today. So have a wonderful weekend for preparing your test 3. Okay? Yeah, you are. What do you have? Let me share our link for attendance first, before I answer your question, you are. So this is our link for our attendance.